Okay. So this is the best which we can do. If you all have any issue right now, please mention that in the chat. We'll start the session immediately. Is that clear? All right. Okay. So I hope all of y'all are doing well. I understand this is a very stressful time for some of y'all, that you'll have to stay home, without much physical contact with anybody else on the outside. If you all have any issues, you all should always reach out to your friends and family, and of course, we are always here to help. I hope this live session is going to be useful. As you know that the entire semester is going to be shortened because of this global pandemic, and we have to make the best do of it. So we'll be holding some sessions of this sort live, and if you all have any issue, you all should always come and you all should always get in touch with the faculties, and we'll be always ready to help. So today's session is the continuation of our syllabus. So where we left off was the Rankine cycle. All right. So the next part of the syllabus which I would like to cover is refrigeration systems. Okay. Now you all have done basics of refrigeration systems before. Yes, you all have done it last semester. You all went through the basics of it in the laws of thermodynamics. So you all know a refrigeration system is a system which basically absorbs heat from a lower temperature device and rejects it to a higher temperature device. Okay, so our basic the way we represent a refrigeration system is you have a higher temperature thermal energy reservoir, so TERH. That's the thermal energy reservoir at a higher temperature. You have a TER, that is a thermal energy reservoir at a lower temperature. And you have a device which works, let's call it R, which absorbs heat from the lower temperature device and rejects it to the higher temperature device. Now from what we understand, from the second law of thermodynamics, specifically the Clausius statement, that this device cannot function on its own. That is, you require provided some amount of work input for this entire setup to work. Is that clear? Okay. So again, we have seen this we have performed experiments on all of these kind of systems, heat pumps, so on and so forth, in your practical sessions. So this is not a very novel concept to you. Yes. Now, how does these systems actually work is what we are going to understand today. To do that, I want to revisit the concepts which have been already done in your previous sessions. That is in Rankine cycles. Okay, so we'll just look at the Rankine cycle before we draw parallels to the Rankine cycle, from the Rankine cycle to any refrigeration system. All right. So what is a Rankine cycle? Rankine cycle is a power generation cycle. Yes, it's primarily used in power generation systems. So in thermal power plants, nuclear power plants, solar, in some sort of solar power plants, you're using the Rankine cycle. And what are the four major components of a Rankine cycle? So you have a heat input device or a boiler. Let's call it a boiler, where heat energy is supplied to your working fluid. Now this working fluid then exits the boiler and goes to a expansion device, which is known as or in this case what we use is a turbine. Okay, so it goes into a turbine. Now from the turbine, you have work output, also known as shaft output, and the working fluid, now which is expanded to a lower pressure, lower temperature, exits and goes into a condensation device, which is again a heat exchanger. So you have a condenser which rejects the heat into the surrounding. So this is Q out, this is Q in. Okay, so now you're rejecting the heat and the working fluid is then sent back to the boiler. Now how does it get sent back to the boiler? This is the higher temperature and higher pressure. So now you have a pump here. You have a pump which pressurizes this. Of course it does it isentropically, reversible isentropic process, and it goes here. So this is our basic Rankine cycle. And now if you look at a TS plot of it, this is your bell curve. So we start here at point 1, which we assume it is in the superheated region. So this is 1. This expansion is reversible and isentropic. It's vertically down. Then is this heat rejection, constant pressure heat rejection. So it goes on till here. This is 2. This point is 2. This point is 3. And this point is 4. So we'll just trace this point here. This is going to come as 3. Then 3 to 4 is again constant isentropic compression. So this is vertically upwards to point 4. And then after this constant pressure, heat addition. So this comes here like this and here. So this is our Rankine cycle. Alright. So now if you look at the Rankine cycle and I ask you a question, where in the Rankine cycle will you have the least amount of energy in the working fluid? If you look at the Rankine cycle and you think about it, where in this cycle do you have the least amount of energy? Now if you really think about it, you will decide that this is the point. Why? If you look at here, it gains all the energy from your boiler. So before it gains all the energy from the boiler to perform this entire cycle, you will have the least amount, not here, sorry, here, before the pump, here. Before it gets work input from the pump and before it gets heat input from the boiler, you will have the least amount of energy. This point here, point 3. Okay, so we start here and what we do is basically reverse this entire cycle. What we do is we are normally working this way. Now what we are going to do is that we are going to reverse this cycle. We are going to reverse this cycle. So wherever there's work output, there's going to be work input. Wherever there's heat output, there's going to be heat input. And wherever there's going to be heat input, there's going to be heat output. Okay, so we start here. We basically have reversed this entire cycle. So we start here at point 3. So we have a working fluid which is just about to boil. Now, in normal circumstances, what is happening is that once you come from 2 to 3, you're dumping heat outside. You're dumping heat outside. So now what we are going to do is we are going to reverse that. What we are going to do is we are going to reverse that and we are going to be absorbing the heat. We are going to be absorbing the heat. So we have a working fluid which is in liquid state at this point of time. And now it is going and it's boiling. So it's from 3 to 2. Now it is boiling. Okay. So from 3 to 2 it is now boiling. Now at 2 what we are going to do, instead of extracting work output, we are going to insert work. We are going to put work in, and instead of a turbine, now we have a compressor. We have a compressor. So this is no longer turbine, now it is a compressor because it's working in reverse, right? Everything is in reverse. So now we are inputting work and now the pressure is, the temperature is rising, the pressures are rising, constant entropy again because this is a turbine now. So we are, in this case it's a compressor, so it's doing compressive work, isentropic compression. So it goes from here till here. And now you reach a very high temperature and very high pressure. Constant entropy again 2 to 1. Okay. At 1 what we do is now originally it was in a boiler. You came out from the boiler. So you absorbed the heat at a higher temperature. Now in this case, you'll be releasing the heat. You'll be dumping out the heat. So from 1 to 4, what you're doing is that you're dumping out the heat. Okay? And then you're going to reach point 4.
Why it is reversed?
Why is it reversed? Okay, that's an excellent question. We are just drawing a parallel between what we already know. In real life, you cannot always reverse everything. As you always know, you cannot unbake a cake, you cannot do all of these things. So in this case, what we are doing is that we are drawing a parallel between what we already know and trying to understand how the system will actually work. Is that clear? So we are using the Rankine cycle as a starting point to understand refrigeration systems. Is that clear? So now again let's start. We start from point 3. We start from point 3 where our energy levels are the lowest. Now we take this low energy fluid and we're passing through a condenser or this heat exchanger here. Now instead of in a normal Rankine cycle you're dumping heat out, here you're absorbing heat. You're absorbing heat. So now that this is causing the phase change of the substance. It's causing the phase change of the substance. You're going in this direction. You're changing the phase from liquid to vapor. At 2, you have some amount of vapor, some amount of liquid. Then you're passing that into now it is an opposite of a turbine. Now it is a compressor. So instead of giving out work, you're taking in work and you're compressing this working fluid from 2 to 1. You reach 1. Now you have reached the highest temperature and highest pressure here and highest energy level here. Now what you're doing is that instead of boiler where you're absorbing heat, now you have a heat rejection device at a higher temperature. So now you're rejecting heat out. So now you're rejecting heat out and again there's phase change. So gradually there's rejecting heat out like this. It goes here. Now it starts changing phase here till it reaches 4. At 4, you're here. And pump, what is the original function of a pump? The pump basically pressurizes this. It pressurizes it from 3 to 4. So opposite of pressurizing, you're expanding it. So as you expand, you move from 4 to 3. Now, our refrigeration systems basically function the same. Our refrigeration systems basically function the same. There are 4 components. 2 heat exchangers and 2 devices which change the pressure. 2 heat exchangers and 2 devices which change the pressure. So we have the fun bit, which is the evaporator. We have the fun bit, which is the evaporator, which absorbs the heat from the surroundings. Now this is equivalent to your condenser. This is equivalent to your condenser in the Rankine cycle, where in the condenser it was giving out heat into the environment. Here now you're absorbing heat from the environment. Is that clear? So now this is your refrigerator space, you're absorbing heat. So again, let me plot the TS chart here for you. TS plot for you. This is your starting point. Let's call this 1. Let's call this 1. Okay? So this is 1. Now we are absorbing heat. So the liquid refrigerant is now boiling. So there's a phase change process which is happening here. So it boils from 1 to 2. Is that clear? Yes? So it expands, it boils here, it changes from liquid state to vapor state. That's why it's called evaporator, because your liquid refrigerant absorbs the heat and is gradually changing into vapor. Is that clear? So you have at 2. Now again we saw that this is now your in the Rankine cycle it is before your condenser. So before condensation, what happens in the Rankine cycle? You have your turbine. Now here instead of turbine you have an opposite of turbine. You have a compressor. So here from 2 to 3 or 2 to 3 is a compression process. Constant entropy compression. Alright? Constant entropy compression. So you have a compressor here. And there's work input given here. Is that clear? So now you have got work input given into your compressor. Here your temperature rises, entropy remains constant. Your enthalpy of course also rises.
The heat absorbed is enough to heat the refrigerant?
Yes. Now you always carefully select whatever your refrigerants are. So your refrigerant is not always any other working fluid. It is a carefully selected substance. We'll get into that. We'll get into the requirements of refrigerators. So the refrigerant is at a pressure and temperature such that when you introduce it into the evaporator, it starts boiling. It starts boiling, and during the process of boiling, it absorbs the heat from the surrounding and converts from liquid phase to vapor phase. Is that understood? So very good question. Yes, the heat is enough. That is one of the properties of your refrigerants. Is that clear? So now your process is moving from 1 to 2, that is evaporation, then 2 to 3, which is your compression. So you have your compressor, that's the noisy bit of your refrigerator or any ice plant or whatever you have seen, any refrigeration device. That is this process. There is a compressor that increases the temperature, increases the enthalpy at constant entropy. Okay, again reverse of whatever you have already studied. It's reverse of your Rankine cycle. Understood? Now at 3 you have got the highest temperature and high pressure vapor. This is in your superheat